Okay, it's 2 o'clock. I promised to start on time, so let's go. The next speaker is Tom Wise.
Okay, good afternoon, everyone. So today I'm going to talk about the work that I did with Willy on polarized thermal velocity hydrogen deuterium beams, storage cells, and atomic beam optimization. So these are just some various pictures that appear in my talk, and some of the, okay, so the IUCF cell is hidden by Sterling Hall, but that's okay. And I actually have a copy of the Hermes cell right here on the table. If you want to look at some of the gory details, it was a big deal making that cell. That was quite a thing. So I'm going to first start talking about storage cells. And this was an idea that was put out by Willy. You can see the concept is pretty simple. Every time a particle hits a wall, it has a chance of going through the path of the circulating beam that's going through your tube, and so you get an increase in the target thickness. The price you pay is that the target is longer, and the density is not uniform. The polarization is not uniform if there's depolarizing wall bounces. And a few other odds and ends. It depends on the temperature. You have to pay attention to that. You have the thick walls. So if you have reaction products like alphas, you're going to have a problem because they're not going to get out. So you're restricted to some of the reactions that you can look at. This is the first storage cell I think that was ever done. It was done in Sterling Hall. There was talk about this a little earlier this morning, I believe, and this was a glass cell. And unfortunately, it didn't survive the move to my current office, but I used to have this in my office, that particular cell, but it's gone now. It had little Teflon windows on it here to let the alphas out. And that particular one showed that you could preserve the polarization. So that was very, very encouraging. The conductance of these cells goes like d cubed over L with a little correction for the end effects. So I've shown here in the density profile that it extends out beyond the length of the cell. That's what this factor here is all about. And there's a little bump where the atomic beam comes in. So you can get over a factor of 100, and you can improve by your target thickness by lowering the temperature. So that's nice. The problem is that then the dwell time on the surface goes up and you can depolarize. And since the figure of merit is proportional to the polarization squared times the target thickness, as soon as you start losing polarization, you're done in terms of cooling. And as soon as you increase the length to the point where there's too many bounces, or you reduce the diameter so that the D over L ratio gets too high and you get too many bounces, you're going to lose right away too. So one of the challenges is to balance the maximum target thickness while maintaining the polarization. Well, that's a lot of fun. And so Scott Price, who's here, had his thesis on a lot of the studies. And basically the outcome was that either use Teflon or dry film. And you hold the temperature around 100 Kelvin. So we built a lot of these. The Hermes cell you see here, I'll talk about that first. You have the beam from Hera coming in. Whoops, wrong button, sorry. The beam from, electron beam from Hera is going through this way. There was a acceptance window above and below for the beam. So this archway that was round for the longitudinal cell had to be flattened for the magnet, but it couldn't be too high because otherwise, I mean, too low, because otherwise you'd be in the way of the acceptance. So we had a really big problem getting the field uniform over that wide area. That was a long study that went on at PSL. We got it though, we got it right, and we avoided depolarization that way. We learned the hard way that we had to put in these little bumps. And it turns out that when the beam is being injected, you would heat this thing, and the heat would be so much that it couldn't be taken away from the thermal conductivity of the thin aluminum. So these little dimples, which are above and below, on top, right in the same place, allow expansion to occur without permanent deformation. So this cell would expand thermally, and then after injection, it was after they cooled the beam and got things calmed down, then it would come back to normal. And during that time, of course, we're looking at the atomic beam sampling. So that was done right here, and we could monitor a lot of the things going on. You can see the scale there, and then this whole thing was mounted on a cooling rail system with helium gas. And so atomic beam coming in here, 10 millimeter, and the sample tube, which started out at 5 millimeters, and then that was too small, so we increased it to 6, which was quite an increase actually in flux because of the DQ. We built one for NECAF. These are the so-called pion cell at IUCF after the thin wall Teflon cell that I think was Hans's design. And I still have my loss. We had a design contest going on, and we knew that we had to have almost nothing in the way of the particles coming out. So I had this idea of taking tension wires and putting foil on them. Unfortunately, the catenary curve was such that you couldn't really do it right. But Hans did this one, and that was great. But then later on, when we were looking at pion production, we could afford a thicker wall, and we also had an azimuthal detector, I believe. So I made this. You should see here, this one, somebody at IUCF said, "Hey, this is really neat," and touched it. Well, it was 25 micron aluminum. So that was the end of that. It took us 2 days to fix that. I fortunately brought a spare with me. But 25 micron aluminum being formed into a tube and then spot welded to these thicker things with this little unpolarized thing here. It was quite a project. And then shipping it from here to IUCF was also, I had to build a whole bunch of stuff just to keep this from falling apart during shipping. Okay. And then we built multiple versions of the Hermes one. And then there's the one, I built one for Bates. I don't have a picture. I don't know what it was like anymore even. Okay, whoops. Somehow we lost the ability to go up and down. Okay. All right, now this is a picture of it. You can see the rails, the cooling rails are not here, they're here. And the target was clamped to them with a whole series of bolts, which you can still see. And these are the helium lines. This thing was cooled with helium gas, and so this was allowing flexibility. This was a stainless steel to aluminum friction weld transition, which is really fancy. And we would weld the aluminum part to the aluminum rails and weld the spiral stainless steel tubing to that side. And that's how we got the transition from a stainless steel vacuum system to the aluminum that we needed for the low Z in the ring. And we built, this original one was 29.8 by 9.8 ellipse. Then we said, not enough target thickness. We went to this side, it was too small. And so then we went, and all the cells that were, most of the data were taken were that size. So I had to build a different jig each time, and it took a long time. And Willie was just kind of watching me do this stuff. He was amazed, and I was amazed I could do it. So everybody was happy. All right, so at Hermes, it was stunning how well this target was studied. Look at all the magnets we've got here. We had the dissociator, the first group of 6-pole magnets, 2 RF transitions, 2 more 6-pole magnets to focus the beam down, another 2 RF transitions, the longitudinal field, and then the sampling, a detector to measure the target thickness at so many degrees off axis, and then the bright Rabi polarimeter here. And with all these RF transitions, you could put this target cell in just about any polarization state you could imagine for hydrogen and deuterium. And there were all of these analytic studies that were done, mostly by Christian Baumgarten, I believe his name was, where we do collision age distributions and atom survival probabilities along the cell. This cell was studied to death. It was unbelievable. I really enjoyed it because I was so impressed by how you could just take some simple observations and keep grinding away at them and getting more and more out of it. And this gives you an idea of all the states that we had and calibrating all the transitions. And a big, massive matrix was made and solved. It just took a lot of RF switching. It was really very impressive. Now, meanwhile, while that's going on, we had the targets at IUCF that were being run all the time. But then towards the end, one of the questions that came up was the molecules, because we knew there was recombination and they were in the cell. They were slower to get out, so they were enhanced by a factor square root of 2. Did they have any polarization? So I was spokesman on this experiment, and we built a cell in Madison and tested it. And it was, whoops, pretty fancy. It had a valve in here, Teflon valve. So atomic beam coming in, this is tapered so that no atomic beam would hit the wall. And you would either hit this Teflon and bounce around and be in here, or if the valve was open, it would go inside this copper mesh line recombiner. And then because the atoms couldn't get out, except for back out, they would then become part of the target again. And you could compare the yield. So it relied on the spin correlation coefficient AZZ, which was known to be very large. And we had a longitudinal field with a superconducting magnet here. So that way you could look at AZZ. And you compare the yield with molecular polarization, with recombination going on or no recombination going on. And this is the results that we got. And when I say we, I mean really we, because the whole facility at IUCF was at our disposal. We had everything. We had the ring, we had the accelerator people, we had the technicians, we had, I brought a couple of things into the shop to make, and all these people were taking data, and it was really, it was the first experiment that I had really been in charge of, and I was very, very impressed by it all. So we had a ratio between the polarization with no recombination to the polarization with recombination of about 0.38, 0.4. Now you might say that's not very much, but you have to remember that when you're recombining, the volume density in the target cell is very low. So there is no volume recombination, none to speak of. Because for volume recombination, you have to have 3 particles hit at the same time, and then one comes off. But if you have 2 atoms colliding in a vacuum and bouncing off each other, they cannot recombine because the energy can't be conserved, the momentum can't be conserved. So you need to recombine on the wall. So you're recombining with a hydrogen atom that's been sitting on the wall for a very long time and is clearly depolarized. So the best you could expect to get is 0.5. So this means that the atoms that were polarized lost very little of their polarization in the presence of a strong magnetic field. And then we had, I think it was Thad Walker, helped us calculate the critical fields for these molecules in the different hydrogen states, the hydrogen molecular states. That was really important to analyze the data. And oh, that was one of my favorite experiments, actually. Okay. So the rest of the talk, I'd like to talk about atomic beam development with Willy. And there was a point in time when there were 4 atomic beam sources running, all within a small sphere. We had 1 down in the tandem. We had 2 in the blue room, which was now an HVAC facility. But, and then next door, Jovan Brown was trying to rework Willy Grubler's ABS. And there was a day when all 4 of them were running and people were doing things. It was pretty incredible. All right, so we didn't want, I guess Willy said that we needed more target thickness in the storage cells. So we wanted more. And I remember at one point we actually got an instrumentation grant from, I think it was from DOE, to work on the first atomic beam source that Andy Roberts, Willy, and I worked on. And that source, when it was finally developed and tested, was sent down to IUCF and became the basis for all the targets that Hans Otto Meyer was talking about and all those experiments, including the molecular experiment that I just talked about. And at that time, it broke the world record. Well, somebody surpassed this for a while. But the problem that we faced at the time was that the magnets were too weak, the atoms were too fast, the degree of dissociation was low, there was too much gas scattering in the beam, and nobody really knew how to optimize the magnet. And all these problems are all coupled with each other. It was a very difficult problem, actually, to optimize this. So I remember spending many, many hours in Willy's office. And then there was such a big problem that we couldn't tackle it all. And Willy and Erhard Steffens, who's here, he had a test facility also, and we split the basic studies. I think we focused more on the gas attenuation, and Erhard was thinking about velocity distributions and magnet development. But then we did most of the trajectory calculations and that kind of stuff. So just to go back for a little bit, 1927 was the first atomic beam that I know of. And these guys had a Woods tube-like dissociator. They had a little hole here to let the gas out and made a beam and had a strong dipole and used molybdenum trioxide to look where the beam was, and they made a jet like this. So that was kind of fun. And these folks, in their paper, if you read it, already knew that you should put oxygen in the discharge. And I remember there were people that were saying, oh yeah, we got to learn all this stuff. And this was already known in 1927. But it turns out that oxygen is critical because of water and OH ions and surface recombination and surface depolarization and all that. Water is just critical, critical, critical. So this is from the Bible. Whoops, keep hitting the wrong button. Continuing to hit the wrong button. So you have polarization versus critical field for hydrogen. You have the RF transitions. This is one of the more modern types of RF transitions. This is a resonance circuit here. This is a capacitor. And you actually have RF that's injected into here. And this is a resonator. And you tune the capacitance so that you have electrons sloshing lengthwise back and forth along here. And the coupling is such that the other side does the same thing. And so you have currents going in opposite directions. And then the magnetic field is first like this, and then this, like this, back and forth. That makes the RF for the strong field transition. And then for the weak field transitions, of course, you have longitudinal oscillating magnetic fields. And these ground cylinders here are to truncate the RF so that you don't get secondary transitions as the field rolls off. You can get multiple transitions, and it really lowers the frequency. By adding these truncators here, the efficiency of the weak field transitions improves. And you can get up to 96% polarization in theory at 120 millitesla, which is about where Hermes was running, I believe.
You want to go out? Come on, I'll push you out a little bit. Sure. You want to go out?
Could you kindly mute yourself? Thank you.
Come on. Go out.
Gelb and Kim.
Please mute yourself.
Did a surface studies back in 71, and they determined that 110 Kelvin was a pretty good temperature. And we later realized that that was all water. And so may help some of you understand why water is so important, because it's really, really keeping your recombination down. Also, your depolarization, which is a little more complicated. Here's your basic atomic beam source. You have, you have a discharge. And if your discharge is too strong, too much RF, then it goes into the nozzle and heats the nozzle. So you have to have a drift length. And one of the things that was done for the RIC source is this temperature here, instead of just being water, was controlled. And that puts you back closer to the optimal 100 Kelvin. And that made a big difference. Then you have a skimmer, 6-pole magnets, a drift length, which is not obvious. A lot of people thought this would actually hurt, but it turns out our studies showed that that drift length improved the beam intensity. That was great. And then you have your arc transitions and then a few other things that are missing. And 13.56 megahertz, although at RIC, I think they could do anything they wanted. And so they put a variable frequency in there. And I think they ran it somewhere between 13 and 27. It was optimal. It took a long while to find that, but it doesn't matter too much. It's very flat with RF frequency. All right, so this is one of the things that happened in the modern sources. We went from inductive to capacitive coupling, so your discharge is right in this capacitive zone. We controlled the nozzle temperature. We controlled this temperature. And then we segmented the magnets. Oh, we used a high purity aluminum nozzle, and we added the right amount of oxygen. And then the magnets being too weak was the big calculation. It took forever. So we had the magnets. What did I do? We had the magnets that were segmented to help the pumping, and we had stronger magnets, much stronger magnets. And here we go. These are these incredible magnets, the neodymium iron boride, based on the Halbach design. We didn't have very much to do with the original design of these. All we did was specify the geometry and the length of the magnetic fields. But the development of these magnets was done by Erhard's group. I forget the name of the guy who was really pushing that there, but there was a long study of that. They did some simulations, and these magnets are just incredible. They ran the pole tip up higher than anybody had ever seen before in a small diameter. So you have huge gradients, and that gives you high focusing forces. The gradients go sky high as the diameter gets small. So you can start out with a small diameter and taper the magnets and get a lot of focusing in the beginning. And then they have to be canned because the atomic hydrogen attacks the neodymium iron boride. They were pricey, but they were worth it. They were really, really worth it, because without it, we wouldn't have the intensity. Well, then this still wasn't enough at some point, because we were invited to give a presentation for Rick, and they wanted a jet target. And this 6 times 10 to the 16 atoms per second was not enough, the one at IUCF. So we agreed to do the whole thing all over again. And I came up with this equation. I inherited this equation from Wolfgang Korsch, but I did this one. And there's a lot of factors in here. The 1.15 is the peaking that we observed by using H2 test beam, attenuation versus flow and temperature, all this data we collected, including what would happen if you had an extra pumps. This is too bad this plot's missing here. This is kind of an interesting plot of the log of the intensity versus what you would expect if you had infinite pumping. And we could predict accurately how much improvement you get by adding a pump at each stage that way. And then the last part was the alpha, and that was from data that we combined with the data that we collected in from this source, plus more data that came in from Heidelberg, and the velocity distributions came in from Heidelberg. And so we put that all together, came up with a plan. The putting it together, though, wasn't so easy. We had to do long calculations, 50,000 randomly generated systems. At first, you have, think about this, it's pretty amazing, 17 parameters. If you have 5 values of each parameter, you have over 10 to the 11 systems. So it's just hopeless. So we had to start out with a much simpler problem, and we just threw random problems, random sizes at this, different tapers, different diameters, different lengths, came up with a pretty decent idea of what we wanted. Then we restricted that and went over to this general geometry and varied all of these parameters. It kept running, and we would throw out systems that were like in this range and keep the ones like this, and that would restrict the geometry, and then we'd run it again, and we just homed in on this thing, run after run after run. And it worked. We got ray trace calculations like this, and you can see the effect of the long drift was to include atoms that would not have been included. You can see it here. These atoms, there's a few of them in here that without this long drift region would not have been in the target region. And then we have a simplified Bright-Rabi polarimeter. So I was not going to have 15 different RF states. We didn't need them for Rick. So we were able to have 2 RF transitions, and you could run them together or one at a time or neither, and get the combinations that way. And it turns out that because of the calculations because these efficiencies of these transitions were so incredibly good, that we could get the polarization of the beam, and this was enough data to determine the polarization of the beam. So to a very high accuracy. So that worked really, really well for Rick. All right, 2 minutes. All right. Yep. Here's an RF transition. Here is the velocity distributions for RickJet, for COSY, for Wisconsin. This is the atom velocity, and you can see what we did for the RickJet was to really increase the lower velocity half. You can see here at both the Wisconsin source and COSY, there was this second peak here, but it was sort of malformed, and so we brought it in closer, so it kept the velocity distribution narrower, and we raised it up, and we wound up getting a jet profile that was very, very tight, and everybody was happy. We got 10 to the 12.4 times 10 to the 16 atoms per second, 1.3 times 10 to the 12 per square centimeter density, and 6.5 millimeter full width half max. And this was data that we got, actually real data from Rick, where they actually moved the whole atomic beam source stand. We kept Rick fixed, and we would move the whole stand in increments, and we actually generated that profile. So that's the real honest to goodness profile of the density. And then also these are different velocity profiles that we were able to study. So the important thing here is that we got enough thickness to measure the absolute Rick proton polarization in one fill, which was a major effort, because they didn't have to compare one fill to the next. Once they got things set up in Rick, they just let it run, and then we told them what the average polarization was for that run. And they were extremely happy. And I was told this morning that this source is still running at Rick. So I'm really happy about hearing that. Okay. And we got more beam than we expected. So I think we were a little lucky. We got steeper and we got a little bit more lower temperature, which helped. And I believe I'm getting roughly out of time here. And there's the Rick source, and I'm sure Yusuf will talk more about that. And we had other things to do at Rick. We had magnetic fields. We had to meet all of these criteria, and it'd take you a while to understand how all those could happen at the same time. But there was a guy at Brookhaven, Wujing Meng, who just was dedicated calculator in magnetic fields, and he saved us. He really came up with some really great ideas, and they all worked. Oh yeah, and so this is what I do now, and it's made possible by Willy. So this is spring green. This is spring green. Actually, they're all spring green. Thank you very much.
Thank you very much, Tom. An interesting talk. I'm sure there will be questions.
I'm the next speaker. Just a comment. Erhard Steffens. Tom, you mentioned me as the main pusher for the magnets for these sextupoles. The main pusher was the Munich group, Gerhard Graf.
Yes.
And Peter Schiemens. Peter Schiemens was really the guy who
That's right.
worked on this. And so he built the...
They were a real technological marvel. I mean, they just really, I think they surprised everybody at how well executed those magnets were and how well they did what they were supposed to do.
But the hydrogen jet you designed for Rick, I mean, this is really, I mean, you need fantastic, you did already fantastic projects, but this is really your masterpiece.
Yeah.
You can be very proud.
Thank you very much. That was
Tom Clegg
Erhard Steffens.
Tom had a question.
Tom Clegg.
A historical question. When we first started running the first atomic beam source here, when I came here, the dissociator had input gas lines, which went through little valves, which we bubbled, that were deuterated water and water.
We used water.
And the mystery was that if you turn on, make it go through that bubbled water, we always got better dissociation. Do you understand now exactly why?
Yes. So it was known at the time, even though by other people, even though we didn't know it.
I didn't know.
There's OH ions that are formed, OH minus.
Just in the by the water bubbling through the by the gas bubbling through the water.
You need oxygen. So you can get oxygen there either by bubbling it through water and getting some water vapor.
Okay.
Or by taking pure oxygen and putting a little valve there and controlling the amount. It doesn't matter.
Okay.
You get OH minus.
Okay.
And the OH minus catalyzes the dissociation of the molecules.
I see. Okay.
And in addition, you get water, even if you put in oxygen, and that, if you have a cooled nozzle, will freeze on the nozzle and keep recombination from happening on the aluminum nozzle.
Okay. I didn't know that. Yeah. I don't know whether Peter Schwant knew that.